Welcome back, everyone. This is the second week of Earth Observations for Disaster Risk Assessment and Resilience. So last week, we had an overview of NASA remote sensing data as well as socioeconomic data from CDAC for disaster risk assessment. Today, we are going to focus on using some of those data sets for actually doing disaster risk assessment, and we're going to focus on cyclones and floods. We'll be using NASA remote sensing data we talked about, as well as we will use CDAC data that we saw last week also. Just to remind you that there is a homework posted today. There will be another homework that will be posted after the last session on week 4. And those of you who want certificate of completion would finish both these homework and submit that via Google form. The link can be found on our website. And the certificate of completion will be awarded at the end after 2 months after the completion of this webinar. So we'll start with today's session. What we're going to cover today is examples of hazard assessment based on past data and which we can use for DRA. And then we're going to focus on demonstration of a few tools and accessing past data and see how we can use these past observations to assess hazard for specific locations, and then applications of this past hazard information for near real-time and future disaster risk assessment. So what we will do is we will have some examples of existing websites. They use past Earth observations and provide hazard assessment over specific regions. And then we will actually use some of the data sets that we saw last week and go through a procedure how to come up with hazard assessment for DRA. We're going to focus on 2 cases. One, cyclones over Mozambique. So assess risk of cyclone over Mozambique, and then again, extreme rain and flooding over Houston. So these are the 2 cases we're going to focus on. Just to recap what we did last week, today we want to look at past data for hazard assessment. And so hazard, we talked about, it's a phenomenon or event that could be natural or human induced, and we're focusing on natural hazard, which cause loss of life, injury, or other health impacts, property damage, social and economic disruption, and environmental degradation. And they are characterized by location or geographic area, its intensity or magnitude, frequency or return period, probability of occurrence. These are the parameters used to define or characterize hazard. So that's how we defined it. We saw last time. We saw that for actual disaster risk assessment, in addition to hazard assessment, we have to have exposure and vulnerability information. So what is exposure? It's the situation of people, infrastructure, housing, other capacities, and tangible human assets located in hazard-prone areas. So exposure can be measured by number of people. We saw last time in the presentation by CDAC, different type of population by gender, by class, by age. So these are exposure information. And to estimate quantitative risk associated with a hazard, exposure measurements can be combined with specific vulnerability and capacity of exposed elements, as we saw last time. So what we are going to do first is we see some examples of hazard assessment from past data which can be used for disaster risk assessment. So here is a website that uses past data for extreme temperature hazard assessment. This is climate.gov. And you can see that in this example, it's for month of July. The data are used from 1981 to 2010. And this is the departure from a mean temperature. I want to show this site to you just so that we can see how one can assess this hazard for extreme heat. There are data snapshots. You can see multiple panels here, but clicking on this average monthly temperature, this is for the US first. You can see that there are months and years bars situated here at the bottom of the map. This is for temperature. You have 30-year average by month. So this particular is for, say, you can change month by this. So this is January all the way to December here. And you can change year, and then you can see 30-year average maximum temperature, 30-year average mean temperature, and 30-year average minimum temperature. So maximum, minimum, and average temperatures, they are shown here, average this data based on last 30 years. What you can also do is look at this. This is the current month's temperature, and you can have difference from average. So this one clearly shows where there is more temperature, more than climatological mean and less than climatological mean. And so now going back to the example here, this is month of July. This is mean temperature. This is maximum temperature based on 30-year data. And then these are departures for month of July for these 2 years, 2011 and 2014. And as you can see, in this region, this particular had much warmer temperature compared to climatology. And in 2014, it was much colder. So now one can go back here and examine this data month by month and find out where there may be persistent heating going on season after season in which month. So this allows you to browse data going back and forth in month and year by using this bar here. So you can change year and month by using this, and it gives you, are there areas you see which are persistently warm or cold compared to climatology? And that gives you some idea of where there may be some help needed, or where risk resilience may be needed for this extreme heat or extreme cold temperature hazard. Similarly, there is temperature also given here. This is again based on 30-year average by month. And here you can see different month. You can go back and forth from May, June, July, August. It tells you where there is more precipitation. Here is in inches, and where it says less. Similarly, you can see difference from average. Here, the colors actually, when you see 100%, it's very close to climatology. So all these light colors show near normal rain compared to climatology. Brown is rain deficit, and green is rain excess compared to climatology. So here you can see that, okay, for this particular year, so this is 2003, say, and for August, it was much wetter here. If you go to some other year, it's much wetter over here. And then if you go through this, you can see that year after year, there may be some locations which have deficit of rainfall, some have excess rainfall, and this gives you some idea about where there is precipitation extreme going on in the US. Similarly, the same site provides hazard assessment for extreme temperatures for global temperatures. Again, these 2 months that we saw, July 2011 and 14, it shows departure from 30-year mean, shows much warmer areas over the globe for July 2011 and 2014. Again, this is the same website, and you can go through this exercise and browse back and forth and see how extreme temperatures are changing from year to year. And that gives you information about, where either there is large variability, or there is really not really extreme temperatures going on. So you can design your risk assessment and then risk management based on some of these data. Again, this is the same example I showed for precipitation. Similarly, there is also hazard assessment from past data about hurricane. And this site it's the National Hurricane Center from NOAA. This tells you the return period of hurricanes, and you can see that the numbers are how many storms there are. They're listed in these small bubbles, and these are the return periods in years. And as you can see, 5 to 7 year return period here, this is, and then as you go, this is 25 to 60. And so how many storms occurred, this is based on past data. So this quickly gives you, at a glance, it tells you that, okay, here is the region where you have return period is short, here it is short, here also. And so here is the region really where you have return period between 5 and 11. Here it is a little less. Okay, here again it is much less as you go north. So this at a glance you can see what kind of hurricane hazard, which area are more prone based on past data. Similarly, this is a, if you go to this site, you will see this, and then you can look at this. It's the number of hurricane strikes between 1950 to 2017, and that also shows you where there are, these are by categories. The colors show category, and so as you can see, category 4 and 5 hurricanes are very common over here, maybe a few here too. So this gives you an idea about intensity of storms, number of storms, frequency based on past data, and that allows you to prepare for it. That okay, in next hurricane season also likelihood of hurricane strike is more over here than say over here, so or over here. So based on that, you can design your disaster risk assessment. Here also, this is shown county by county. The darker color show more number of hurricanes affecting areas. And so this is the coastal region. But this site uses past data to give all this information. This is for global tropical cyclone assessment, and this is from this particular reference provided here at the bottom. And this is showing category of storms. It's the locations of lifetime maximum intensity, or LMI, and this is based on the period between 85 to 2014. As you can see, category 3 and above hurricanes, they are seen here, 3, 4, and 5. They're very common in this area and again in this area. Category 5 hurricanes, you can see this purple, where you see this everywhere here, very strong hurricanes. Maybe in Bay of Bengal, but more or less this is 3 and 4. This is 3, 4, and 5. So these are more intense. So based on past data, it tells you, okay, here is more likelihood of strong hurricanes, maybe some weak hurricanes here. And so it also gives frequency if you go to the reference. And then this allows you to design for current and future cyclone hazard for resilience for that disaster. This assessment is about flooding, and this is again from CDAC that we saw last week. What this shows is the deciles of flood hazard. So decile is the population of disaster is equally divided into 10 parts, and so this shows where there is 1 to 4th decile. These are the blue colors, and the red is the highest decile, 8th to 10th. So here are the regions you can see for flooding. And so this, from the past data, this shows distribution of flood hazard occurring everywhere in the world. This comes from based on 85 to 2003 data, a 19-year period. And there is a tool, it's Dartmouth Flood Observatory, that you will find on ARSET website where we talk about flooding. This website is there is a demonstration of this website that you can see where this data are coming from a variety of sources, including remote sensing. And so based on that, you can see globally where there is flood risk going on. Flood hazard is more, and that allows you to prepare for resilience, also for mitigation, for planning. So we saw these tools which provide hazard information. You can visualize those and look at magnitude. Next, we want to look at Earth observations and derive our own disaster risk assessment. So as we saw last week and in some of the tools, DRA would depend on hazard type, geographical area, and socioeconomic conditions. Also, there is no unique methodology to come up with disaster risk assessment. Locally and regionally, a variety of data sources can be used. They have been used if you look at literature or go through disaster emergency management agencies' websites. Number of data sets, in situ data from remote sensing, from models, they have been routinely used. And generally, statistical and empirical techniques are used which are disaster specific as well as region specific. So in this session, we are just going to provide a possible methodology. How can we use past data and look at past hazard conditions to learn about hazard frequency, intensity, spatial extent, etc. And together with exposure data, can we aid disaster risk assessment, which can then help in disaster risk reduction. So here we are just going to focus on demonstration of a possible methodology. It's very important to note that additional data and quantitative analysis will be required for more accurate disaster assessment anywhere for any hazard. This is just an example. And for that, we're going to start with past Earth observation for hazard assessment. As I mentioned earlier, we're going to focus on cyclone risk assessment over Mozambique. For that, the information we require is frequency of cyclones and magnitude or intensity in terms of wind speed, rainfall, and sea level pressure. So cyclone frequencies can be obtained from these websites. So National Hurricane Center as well as Joint Typhoon Warning Center, they have data archives for past cyclones. And so they can be used to see what category, what location, what track, where the landfall occurred. So we are going to use that over Mozambique to see how many cyclones occurred in last so many years. Then we will look at NASA Earth observations. We're going to look at rainfall from TRIM. This is TMPA multi-satellite analysis, and similar multi-analysis product from GPM, iMerge. These two products we talked about last week. We are going to use both of these. And we're going to use MERA2 model, which is a reanalysis model that provides winds and sea level pressure. Next example we will see would be extreme rain risk assessment, and we're going to use example or case study city of Houston, which frequently gets flooded because of either extreme rainfall or because of cyclone related or hurricane related rainfall. For that, information useful would be frequency of rainfall, intensity, distribution in terms of what is the rain rate per hour or per day, and spatial extent. These are useful. They can lead to flood risk assessment. That's why we're going to look at extreme rain. Again, we'll be using TMPA and iMerge for that. Next, we're going to look at exposure data from CDAC. We had a presentation last week, had human population data, roads and infrastructure, coastal zones, human settlement and urban impermeable surfaces. All these data are available. We will be focusing on human population, for example, in this demonstration, and so that provides exposure for any particular hazard. Next, what we will do is, once we know past hazard, where they occurred, what was the intensity, what kind of exposure situation is there, can we use near real-time data and forecast data to come up with DRA? So any approaching hazard or any hazard going on now, can we plan can we assess which area would be most exposed based on hazard intensity and exposure. And for that, again, we can use these operational centers like National Hurricane Center, Joint Typhoon Warning Center. There's also Global Disaster Alert and Coordination System that provides information about cyclones that are occurring now. So if there is any cyclone going on, it's in progress, this site can help with information. These two sites, they provide potential track also. So these can be used for near real-time and forecast data. Also, near real-time rainfall from GPM is available from Precipitation Measurement Mission site, or we will see some other tools which can provide near real-time data also. And then for forecast, we can use rainfall and winds, both useful for cyclone and flooding, for 10-day forecast from this GEOS 5 model that we talked about last time. So we will first start with demonstration of how to download data, past data, near real-time data, as well as forecast data. We're going to use these data for both hazards that we talked about, cyclones over Mozambique and extreme rainfall over Houston. We will start with past data first. So we're going to start with TRIM TMPA, GPM iMerge, and MERA2, which is A model data. TRIMPA and iMerge provide rainfall, and MERA2 provides sea level pressure as well as winds. And these data are available from these two data access tools, Giovanni and Data Information and Services Center, DISC. So why are we using TMPA and iMerge both? First, because TMPA is a long-term data set, as we saw last week. It started in 1998 and it has been going forward till now. iMerge, which started with GPM in 2014, now there is a new version of iMerge. That also we saw last week, that there is a combined TRIM GPM iMerge product that makes data available starting from 2000. And for more quantitative analysis, we recommend that iMerge long-term data set be used. So what we're going to do is do analysis using TMPA, but also look at how to get iMerge data. Now these long-term data are available from DISC. In addition to this, TMPA and MERA are also available from DISC. So for bulk download, for more quantitative analysis, if you want to do calculations with the data, then that is the tool to use and to download data. So we're going to have a demonstration for that. However, what we're going to focus on is to do online analysis and visualization. And for that, we're going to use Giovanni, in which we will start with past data TMPA and then also look at MERA2. Also important to note is that based on past data, we will calculate climatology of rainfall and winds as examples here. Because for any hazard, it is important to know how intense it is compared to a baseline or with a reference, and that climatological analysis provides that reference. So that is the first thing we will do, how to analyze and visualize climatology of rainfall and wind speeds, and we can also do sea level pressure. We are going to focus first on rainfall and wind speed. Next, we are going to look at forecast. Forecast from GEOS 5 is available from this tool. You can go on this site and visualize maps, and we'll also have a way to download these data. Now for this session, for this webinar, we are going to focus on visually looking at the maps and comparing with climatological hazard analysis to see whether upcoming hazard based on forecast how strong it is compared to the climatology. Next, we will look at exposure data. In this case, we will focus on population, and we saw last week from CDAC presentation how to download population data. So we will combine hazard information and population data to have disaster risk assessment, how to aid disaster risk assessment. And as I mentioned earlier, this is just to show a methodology that you can do somewhat qualitative analysis using these tools without really getting into too many calculations. How can you assess hazard intensity and extent, and how can you use that for better disaster risk assessment. To aid that, we will also use QGIS, and we will also use either Microsoft Excel or open source software OpenOffice. Either one can be used. So we will see a couple of examples how to use these to do analysis of some of these data for a good qualitative somewhat, but disaster risk assessment using QGIS maps and using some analysis from these tools. So we're going to start with cyclone hazard. So we're going to focus on Mozambique. So here, I want to start with the demonstration. Here is a site. This is the National Hurricane Center site that we talked about. This provides information globally about storms. I have focused here on Mozambique, and this provides information about past data, past cyclones that came close to or hit Mozambique. This is as you can see, this is Mozambique, and these are all the tracks of cyclones occurred in last so many years. You can pick by years or by storm intensity. For now, I'm going to use year descending. Last year available here is 2014, and then it lists all the storms that are shown here. You can go to each of this and you will see the track, and then you can see, if you go to this advanced features, then you can see the category, which color it corresponds to a particular. So this is extratropical, this is tropical depression, tropical storm, and these are hurricanes of these different categories from 1 to 5 based on wind speed, sea level pressure, etc. And you can choose by timeline also. What I've done is I've picked data, all of them from 2014 to 2000. I've compiled a table based on that. Between 2015 and 19, I've gone on websites, different websites, including AccuWeather websites, and found out what kind of storm situation was in all these years. So we're going to analyze data for last 18, 19 years, starting in 2000. And so here is a list that I have compiled based on this National Hurricane Center site. These are all the cyclones occurred between 2000 and 2019 that actually came ashore on Mozambique coast and affected Mozambique, and these are the dates. One thing to notice in this map is that it is in this part that a lot of storms do landfall, but all the storms that occur here, they also contribute to rainfall and winds over the shore in Mozambique. So compared to that, if you look at those storms, majority of them, they form between January to April. As you can see, most of them, one is January, so these are months. Only one in this record occurred in June, maybe related to the monsoon season, but most of them, they are in January to April, which is the Southern Hemisphere summer season. So what we are going to do is first start with climatology for these months. Can we get rainfall and wind climatology for these months, so that when we go to these individual storms, we know how strong we can assess the intensity and spatial extent with respect to the climatology. So for that, we're going to first calculate climatology of rainfall and winds. And for that, we're going to first go to Giovanni. So this is the Giovanni site. Those of you who have taken ARSET webinars before, especially in disasters and water, we have used this site often. You can search data by keyword. So for climatology, let's start with TMPA rainfall, search. And here you can see there are monthly, 3 hourly and daily data. For calculating climatology, we can use this monthly data, that's easier. However, what we are going to do is change this rain rate to millimeter per day, because we want daily climatology. daily climatology, so that for storm, we can compare daily rain rate with climatology. You can do this every hour or 3 hour, depending on the data availability, but that just requires more calculations or more data analysis. We're going to start with daily climatology. And so here we also are going to choose Mozambique. You can choose it by map. You can draw a box over Mozambique, or you can choose exact shapefile for the country. Going here, you can type Mozambique, and as you can see, once you choose, it highlights the country, and that's where we will get the data. So this is a good way to do special subsetting. Now we're going to use monthly and seasonal averages. This is the climatology part that we're going to use. And for that, for now, we are going to go to just January, February, March, and April, where most of the cyclones occurred. So rather than going to all the months, for now, we're just going to focus on these 4 months. And we're going to pick 2000 to 2018 as our baseline or climatology period, a long-term average period. So we are going to average data over Mozambique rainfall for in millimeter per day climatology, and then we can just say plot data, and it provides, I've already done that to save time. So here is the climatology of TMPA rainfall. As you can see, this is January in millimeter per day between 2000 to 2018. Here is the scale, and if you scroll down, you will be able to see all other months. So this is February, this is March, and this is April. As you can see, but just by visualization, you can see that here there is more rainfall, millimeter per day climatology, much higher rainfall in northern part than in southern part. It's moderate, somewhere in between in the central part. And as you go down from January, February, March, and then April, actually the highest rainfall is in January, about 12 millimeters per day. So this allows you to put overall picture over Mozambique, what happens in long run, what's the long-term average, and this is what is provided. Now you can go to download here, and you have multiple options. You can have netcdf file if you actually want to do you write software and do analysis by yourself, or you can have images, or you can have geotiff files which you can do analysis or further calculations in QGIS, and KMZ, which is just for visualization in Google Earth. So here I have downloaded all the TIFF files. TIFF files, you can just click on the file and save for further analysis, and I have saved these files that we will look at later in QGIS. But by clicking on each January, February, March, and April, you can get this climatology rainfall saved for Mozambique. Next, I have done the same with MERA wind speed. This is wind speed. Once you type wind speed, it tells you all the options, and we are going to pick MERA 2, which is the reanalysis product we talked about. This is surface wind speed, and it says that it's based on maximum hourly wind from the model, and the same analysis can be done here. So we have climatological wind speed based on MERA 2. Once you pick that, and then when you plot data, you can find that you have wind speed data. Here are the plots. So this is average surface wind speed between 2000 to 2018, and please note that the units here are in millimeters per second. So this is for January, February, March, and April, again 4 months. Interesting to note that the wind speed is, of course, in coastal region in southern part is much higher. Everywhere in the coast overall there is high wind speed. In southern part there is higher wind speed than in northern part. We saw that rainfall was larger in northern part than in southern part. So you can again go back and download these data. TIFF files I've already saved just by clicking on each of them. You can save these files and we will analyze these later. But this gives you a baseline of climatological data. So next, what we are going to see now is how to get the forecast data. We are going to look at GES disk. This allows you to do bulk download of data. So same data sets that we saw through Giovanni can be downloaded here in digital form. And why would you want to do that? Because just as what in Giovanni we calculated long-term mean, but suppose you wanted to see map of standard deviation at each point or percentile of rainfall at each point, then you would want to look at digital data. So it involves more quantitative analysis, but if you want to do that for your own region, then this is the tool that allows you to download data. Also, I should point out that you would have to register to NASA Earth data through this site. It's NASA Earth URS, Earth data, nasa.gov. And once registration is required to data download from GES disk as well as from Giovanni, and from most other NASA DACs you can download data if you are a member of NASA Earth data. So here, once you log in, you can search with keyword. Again, you can search with TMPA. RT stands for near real time. You will see multiple different data sets on different time scale. We want daily data. And so this is the data that we are looking at, not the real time, but this is the gauge calibrated final data. You can click on it and you can get more information about this product. For subsetting and getting data, this is the choice we're going to make. Here it allows you to choose time, and to be consistent with what we did with Giovanni, we're going to use 2000 January 1st to December 2018 31st. This is 2000, this is 2018. So for 18-year mean, you want daily data for these years. You can do special subset. You can either enter latitude, longitude box. If you know already, you can zoom in into any area if you like by this plus and minus, zoom in and out. And you can draw a box in the area of interest. I'm going to cover Mozambique and Mozambique channel as well. You can cover that. It also gives you exact lat-lon that you chose here. Next, you can choose variable. Here you have multiple variables and you can read about each and every one in the documentation. The one we want is precipitation. There is error associated with precipitation is also available through the dataset. And so finally you choose file format, could be netcdf or netcdf4. So this is the format you will get the data in. Then you can select get data. Since it is daily data for 18 years, it takes a few minutes to get the data. So it tells you how many files there are. So it's almost done. It starts populating this list here. You can, if you were looking for just a few files, you can click on them individually, and that allows you to save these files on your computer once you click on them. But since there are so many files, we would wait for all the download to be done, and then you can get this download link list. Once you click on that, you can save that as a text file on your computer. It allows you to select directory and file name, and that file then has names of all these files. Once you save that text file, you can go to instruction for downloading, and you can use either wget or curl to download bulk data, all the files. And here is the instruction for Windows, Mac and Linux for wget and also for curl. So once you, just for example, this is the command, say on Mac, I would use on my Mac is wget, and here is the text file that you saved with list of all the data files. So once you run this command, all the files are downloaded on your computer, and then you can use that. You can use any other software to read the data and do quantitative analysis. So going back to GES disk, I want to show quickly iMerge also, because I want to point out something here. iMerge data, as you can see, these data are available for 2000 to 2019. This is version 6. If you see, there is also version 6. So this is the latest version. And you will see 30 minutes data as well as you will see monthly data. There is also daily data, and this is version 6 again. You will also see some version 5, but better to choose the latest version. You can also see other data which are early and late data which are not yet extended backwards with trim data. They will be available, but for now we will be using this daily final precipitation data which are gauge calibrated with rain gauge, and you can go through the exact procedure of what we did of choosing spatial and temporal subsetting. But for variables, now here you will use this precipitation cal, or precipitation which is combined satellite estimates with gauge calibration. So that's the only difference. Everything else remains the same. So going back now, with MERA also there is something to note. You will go to MERA, you will see many options. For winds and sea level pressure, you want to put SLV or single level files and search those. You will get again quite a few options. Again, you can read the documentation online available through GES disk to know more about it, but each file has different parameters, and again you can see diurnal, hour, month. The wind data are available in time average SLV files, and they are available on hourly time scale. So what we will do is look at this is instantaneous single level. If you go here, it is time average 1 hour over time. So if you go in here, then you get the same, and again you can read more about each and every product. To subsetting, you can go through all this as we did, but for variables, now you have many variables. If you don't choose any, you will get all of them. What we want is the closest to the surface is eastward wind, which is it's a U wind, the 2 meter. You can click that. There is also northward wind at 2 meter. Now notice that you don't have wind speed available here. What you have is U and V components. So you also have to do further calculation to get wind speed. There is sea level pressure also. Now this is hourly data. So this allows you to do mean, while here you can say mean, and then start time would be start of the day to end of the day. So based on this hourly data, then once you choose that, you will get daily data. So by doing this get data here, again you will have to choose file format. Here you have HDF availability also, but we're going to stick to netcdf, say, and then you can say get data. You can also choose sea level pressure if you like, and then once you get data, what it does, it goes through hourly file, averages over a day, and then makes that list available to you that you can download by using wget. So this is To do quantitative analysis, it's a little involved, but if you can use any open source software like R or Python or licensed software like MATLAB or IDL, then you can handle these netcdf file and do calculations and develop schemes to come up with hazard threshold, say, or you can just look at standard deviation, you can look at percentile, so that you know that over the area of your interest, what are the statistics of these parameters. So that's why this bulk download may help you if you want more accurate quantitative analysis of data. So what we saw was use Giovanni to do online calculation and visualization, use GES disk to download data, which then you can use for further quantitative analysis. Next, final thing we want to see is how to get forecast data. As you can see, there are maps, multiple maps and information available. For our cyclone hazard, we want sea level pressure, precipitation and winds, and that is available from these weather maps. You can click on this map and get information visually, or you can download this forecast data. You can click here on forecast, data access forecast, and you can see that current month is there and current day is there. Now there are multiple times, initial times from which forecasts are started. I checked these two, but all the forecasts are not done yet. So I'm going to click here, the 00 hour on 5th of August. And once you click on it, it gives you different files which have forecast for next 10 days starting from this time. Here are all the files. For more information about the file name, you can look at the documentation online on Geos5 webpage, or you can go to ARSET webinar about tropical storms, which also has information about it. So this is forecast, instantaneous. If you scroll down, you will see time average data also. So these are two-dimensional data. You will also have three-dimensional data when you go down, depending on the parameters. And what you would be interested in, again, time average, just like we saw in MERA, you want time average data, which is going to be for UV and sea level pressure. Also, rainfall is available here. So now, if you see the file name here, it starts from 5th of August and it goes to almost like this is 6th, hourly forecast all the way to 14th of August you will find in each file category. So this is 10th, go down and then you will see 10-day forecast going up to 14th of August. You can pick a particular day, particular hour forecast and then do the analysis. Or what you can do is download all hourly data for that particular day and then do daily analysis like we did for MERA 2. So for now though, and as you can see, these files are available in netcdf 4. But now we're not going to download the data. It's if you want to do quantitative analysis, you have to, and it's an involved data analysis then. But here we are going to look at maps so that get visual idea of what is going on. You can see precip and sea level pressure, and then winds both are available. The different regions available here. Let's go to global, and you can see here is Mozambique. What you want to, this is precip and SLP. Contours are sea level pressure in hectopascal or millibar, and here the colors are shown as accumulated precipitation in millimeter. As you can see, there is precipitation going on here, not precipitation on Mozambique right now. Also, what you can see is wind speed. Now, when you go to wind speed, it's important to note that there are levels associated with that. You want the closest to the surface, which is 850 hectopascal or millibar. So if you go down here, it should show you 850 millibar winds. And here you can see the colors are actually winds, but what you see here is in knots. What we saw in Giovanni, our time mean plot we had was in meters per second. So to convert these knots to meters per second, it's about 1 knot is 0.5 meters per second. To be exact, it is 0.5144 meters per second. So you have to do that conversion when you compare with climatology. When you download the data, they will be in meters per second also. So this is visually, you can see that there is no storm occurring right now in Mozambique. So this is near real-time data. You can go to a forecast time here, the lead hour starting from today. Suppose we go to say 10th of August, 12Z, then you will get a map of precipitation SLP for 10th of August, 10Z. It is still working on it. I think this is still 5th of August. Okay. So this is valid on 10th of August now. And so you can see that the forecast rainfall is here. You can see a system developing here. Nothing much here in Mozambique. You can look at the wind speed again at 850 hectopascal for the same day. And you don't see much wind picking up. Only here you see some wind picking up. So this is quickly tells you if there is any storm developing. You can quickly see that and compare visually, qualitatively somewhat with the climatological analysis we did from Giovanni to see how strong compared to mean, time average mean, this approaching hazard is or cyclone is bringing rain or wind speed compared to that. So that's how you would use this forecast data to do hazard assessment for future next 10 days, say. So what we've seen now is we've looked at past data, near real-time data, as well as forecast data. Next, we are going to use QGIS to do a storm analysis in the sense that if there is a storm occurring near Mozambique, how would you assess what kind of hazard that is and what kind of exposure data you would use to assess disaster risk for that particular storm. And so that is going to be our next demonstration. So before we start the QGIS analysis of cyclones and their impacts over Mozambique, here's again the table that I showed earlier with all the cyclones compiled since 2000. So what we saw that most cyclones occurred between January and April. So for example, I'm going to pick cyclones which occurred in March, and I'm going to show two examples. One is Cyclone Idai that occurred in March of 2019, a major cyclone causing a lot of damage. This was also shown by Dr. Susanna Adamo last session for CDAC data. So I'm going to show one case study, that is Cyclone Idai. Another one that was Cyclone Chokwe that occurred in 2008. These two occurred in March. So I'm going to focus on these two cyclones. To start with, what I've done is looked at precipitation rate for each of the cyclones. So this is for Cyclone Idai. And here, if I click on the map, I have looked at this bigger box for Hurricane Cyclone Idai movement in this area. And then I have calculated rain rate over the country. So that's what this is showing. And I'm going to go, if you go to map, you can see animation feature for this. It won't work for a shapefile, but for any box, animation feature works. And so I just want to show these results. You can use animation feature to see how a cyclone is moving. As you can see, Idai started here. Finally, it developed again, and then it started its motion inward in central Mozambique, and then it went up again. So based on that information, I have this average rain rate in millimeters per day for cyclone Idai. So that also I've used StreamTMPA, and using Giovanni average map features, this is calculated and then saved as stiff image for analysis in QGIS. This is the time average map again, so average rain rate for cyclone Chokwe that I just mentioned, that was in 2008 March, and so this is the average rain rate for that particular cyclone. And as you can see here, there is maximum rainfall here in slightly northern coastal part of Mozambique, and that also is saved in TIFF format. Last but not the least, this is wind speed for cyclone Chokwe. That is basically, let me go back and show the user input for that. So this is surface wind maximum speed from MERA2. You remember that we did the long-term mean of the same quantity for 2000 to 2018. Now this is just for one cyclone, and I have done the same for Idai also, and all these images have been saved as TIFF images to look into QGIS. So next, I want to focus on analyzing all this data in QGIS. And so the idea here is that you have this long-term mean precipitation and surface wind data. How can you use that to assess hazard impact or hazard intensity of any particular storm? So in this case, we're going to look at two cases, Idai and Chokwe. So we'll start with first all these layers I've already loaded in here. Okay. So what we have is this time averaged precipitation. This is 2000 to 2018 mean precipitation. This is mean surface wind speed. This is Idai precipitation, and we will go to this again. This is Idai wind. This is Chokwe precipitation and Chokwe wind. What you have here is population that Susanna demonstrated last session that has been imported in QGIS also, and you can see that the major population center are seen here. So that gives you exposure to these cyclones, and so now we will go through each case and see which part was more impacted by this particular hazard, and how many people were exposed to it. So here is the mean precipitation, 18-year mean, and here is standard deviation of the same precipitation. If you look at the mean, it goes up to about 12-13 millimeter per day. If you look at standard deviation at each point, it goes up to 5 millimeters per day. It is higher here in southern coastal areas. Here it's lower in the interior of this country. So this is standard deviation, and Sean McCartney calculated standard deviation based on cell statistics in GIS. This mean we already obtained from Giovanni, as we saw earlier. What I have done now is I have created a quantity which I'm going to use as a threshold. So that is, I'm taking this mean precipitation and adding this standard deviation values to it to get this mean plus standard deviation layer. And if you can see the values, they range now from about 3 to 15.5 millimeters per day. Now, this is just for an example. I want to use climatology plus 1 standard deviation value as some kind of threshold to gauge cyclone intensity with respect to normal precipitation. And so when I compare that with precipitation from cyclone Idai or cyclone Chokwe, it tells me which area has more impact. Where there is much larger precipitation than normal, that's where the hazard intensity is high, hazard impact is high. And then you can look at exposure data and vulnerability data, infrastructure or assets in that area to come up with proper disaster risk assessment for that particular hazard. So what I've done here is, if you look at Idai precipitation, you can see that it goes up to about 30 millimeters per day. It's higher in the central part of the country, lower up here north and south. Here is where the most impact was. Now what I have done is I have used raster calculation. So I use raster calculator with different rasters and this mathematical operation to come up with this mean plus standard deviation layer, as well as now I have a anomaly layer, which is departure from mean. So I have taken Idai precipitation and subtracted this mean plus standard deviation layer values from it. And so what I have is this anomaly data. So this is Idai anomaly, and as you can see, it goes from negative to positive. Negative values, they mean that here rainfall was less than mean plus 1 standard deviation, so it was much below normal. As you go up here in the yellowish, greenish and bluish area, it is much higher, several standard deviation higher actually than the normal. So here is where the most intensity of this hazard is with respect to normal rainfall. And so here is where one should focus for disaster relief or for any operations activities that are needed. They should be focused on this area. Similarly, if you look at winds, Idai winds, here they are up to 12 meters per second, mostly in coastal region here. And you can look at them in with respect to anomalies. It's in this area coastal winds are high, and here is where you have much higher precipitation compared to normal. Okay, and so now we can do the same with Chokwe. So here is the Chokwe anomaly, and you can see the values, they are much higher actually. They're like 20.8 over here. Everywhere else the impact is less. The rainfall is not that intense compared to normal, but in this particular area you can see that it was quite intense. So now you compare Idai and Chokwe, you can see how different areas were affected by these two hazards. Similarly, you can look at winds for Chokwe, and here you can see that higher wind speeds are here, but precipitation is not that high. Here there is high precipitation and winds are coastal winds are also high. So these are the regions to focus on for this particular hazard, so particular cyclone. So looking at this past reference and then comparing each storm with that, it gives you idea which area is experiencing anomalous conditions. That's where that hazard intensity is high. Now let's go look at what is the exposure, and I'm going to just focus on a few cities first to have, sorry. Okay, we lost the map here. So here on Mozambique, here is a city, Beira. This is Quelimane, and this is Maputo. So if you now look at the population distribution over this area, you can see that these are population centers with, you have less population everywhere else, but cities are really crowded in the sense per 5 kilometers. You can see that about, these are the red colors, all the way up to more than 5,000 people for 5 kilometers. So these cities are where if the intensity of hazard is very high, exposure is very large too. Similarly, these are also urban centers where population is concentrated, and you can look at the city of Beira, which was affected a lot by the cyclone. This place, coastal city, here is population is about close to about 1,000 to 1,200 people per 5 kilometers. So these are centers of more exposure, and here is where you would focus your, this is the Idai anomaly. If you can see here, here is very heavy rainfall, here is moderate rainfall, but it is affected by this. Now, it is also important to note here is that I have looked at entire life cycle of each cyclone. I've averaged over all the days. For actual disaster response, you would be doing this analysis at every time step when you have data and compare it to long-term mean to see how intense it is, which area have more intense rain and winds. That's where you need more efforts for relief, for rescue. That's where you need to divert activities and resources. So that way, this is just an example of how you can use these different data sets, so and then come up with hazard intensity and its exposure, and then that allows you to do disaster risk assessment overall. You can add additional layer that we saw from CDAC last session to have better idea if there are any dams here, or if you can look at the roads which may be inundated because of this. So these are all different layers then you can put in along with this remote sensing and modeling data to have better assessment of what is going on. Now, also one thing to notice is that resolution here is 25 kilometers or even lower. So obviously it is not a very high resolution information, but it does aid your activities for relief and rescue, or even for future mitigation. If you go through past cyclones and see where there were major impacts, you can come up with strategies to deal with these disasters. So this is just an example how you can start with remote sensing modeling data, look at socioeconomic data, combine in QGIS, and this is preliminary analysis, but you can do it in great detail for actual disaster risk assessment and how to respond to any disaster. So this concludes our cyclone case study. Next, we're going to look at precipitation, extreme precipitation over Houston. Look at extreme precipitation assessment over and around city of Houston in Texas, US. So the idea is that by looking at extreme rain frequency and magnitude, one can assess potential for flooding in this urban area. And for that, we are going to start with Giovanni and using trim TMPA data again. In search TMPA, we are going to first look at monthly data. We are going to look at long-term evolution of precipitation over Houston so that we can find out what are the ranges of precipitation in different months. We're going to pick millimeter per day as our rain rate. So that will be for each month we will get average rain rate in millimeter per day. We're going to pick this monthly data. Now I have already picked the coordinates. This is the box which is centered around Houston area. If you zoom in, You can see the box here. This box encompasses Houston City and vicinity areas. So all the analysis we're doing is going to be for this region. We're going to look at time series and look at seasonal time series. This gives us an option here, months or seasons. We are going to pick all months to see how rainfall changes over this area month by month. And year range will be 2000 to 2018, which is the last entire year. And just to be consistent with the previous case study, this is the range we have chosen over city of Houston, and this is the precipitation. You can plot data and launch the workflow to look at the time series. I already have done that, so I have all these time series here. As you can see, this axis shows years, and each different color, they represent different months as shown here in the bottom, January to December, and here is precipitation rate in millimeters per day. So right away you can see that average precipitation is maybe around 5 millimeters per day over this year. Interannual variability you can see, and this is June, this is November, this is August of 2017. This is because of Hurricane Harvey. You can see this is the highest rainfall over Houston. This is May. This is July. So you can also turn off multiple months and just look at a few months. So from May to August, here is what the pattern looks like. If you want to look at winter months, then January, again, this scale changes as you add month. So January, February, it's less than 6-7 millimeters per day, more or less. And then if you go to May, you have up to 10 millimeters per day. June, here there is 15, 12. July, also you see some years have higher precipitation in August. So to further analyze this and look at climatological mean, what we can do, a long-term mean, we can download this data, and all these files can be downloaded either as netcdf file month by month or as CSV file. I have saved this as CSV file, and let us look at that. Bear with me while I find the Excel file that I have saved. Here is the file. So I'm using Excel, but you can do the same thing by using OpenOffice, which is an open source software. So what you see here in the file, these are years, these are months, and values are listed here. I have used statistical analysis for this so that here I have found mean by using this average. For each column I have this mean values. So this is for January, mean over these 18 years, February, March, April, all the way to December. And as you can see, the values vary from about 2.5, which is minimum in February, all the way to August, it's 4.9. So about 4 to 4.9 is the higher value. Here standard deviation also I have found using this standard deviation function here. And so this is standard deviation over this year, and this here shows standard deviation plus mean. So this I have calculated so that this is some kind of threshold we can decide extreme precipitation based on these values. If for any given day precipitation exceeds this value, so this is mean plus 1 standard deviation, and you can decide your threshold after really understanding the data. This is, for example, I have used standard deviation, so mean plus standard deviation as a threshold. So any day in this, so for say August, any day has precipitation more than 10.2 millimeters per day or about 10 millimeters per day, you can assume that this is way above normal precipitation, and then there is flood likely for that. So now, once you know this, you can actually plot these data, which I have done here. It's not, come on. Okay, thank you. So this is mean in blue, and orange is standard deviation. As you can see, generally May to September has higher value. This is August. Standard deviation is high in August as well. So this allows you to get some understanding of the data. What are the values, mean values, what are the standard deviation, and how can you evaluate any one daily precipitation as higher than normal or very higher than normal compared to these values. So now what we are going to do is go back and look at individual days and see if we can come up with frequency and magnitude of these extreme events. So I'm going to minimize this. What I have done here is I have gone back to TMPA and have chosen daily trim data here in millimeter per day. And now I have this area average time series for the same Houston and nearby areas, and I'm looking at time series for different years. So I have looked at from say 2010 onwards all the way to about 2018. I have August time series. Why August? Because that had the highest precipitation in this period and higher standard deviation also. Hurricane Harvey occurred in August. So just as an example, I'm picking month of August. You could do this analysis for every month. Now, I have done already time series for all these years. So let us look at those. So this is 2010, and from the Excel chart, we know that around 10 millimeters per day is the threshold that we chose. It is mean plus standard deviation is about that much. So rainfall above this value would be quite above normal, and then that there is potential of flooding because of that. So here in 2010 there is one event. If you go to 2011, there is, you can see that none of these events are above 10 millimeters per day. If you recall, 2011 was a drought year, and you can see that precipitation magnitude is much smaller in here. If you look at 12, then again you have a lot of rain here and quite a few. So frequency of higher than normal precipitation is 1, 2, 3, 4, about 4 events. In 13, it's about 2 events, about 10 millimeter, above 10 millimeters. For 14, also you have 1, 2, 3, about 3, and so on. This is 2015. As you can see, this is much higher. So almost all these events are above 10. So that's an anomalous year. If you go to 2016 also, and it's a high year. I'm going to move down to 2018. Here about 10, you have about 1, 2, 3, 4. So if you examine daily precipitation, you will be able to assess frequency of rainfall which are above this threshold that we picked, and then these are the events. You would go back and look at data, in situ data on ground, what kind of flooding occurred, what kind of damage occurred, and that helps you assess extreme precipitation and flood related hazard. So that is one way to look at different frequency and magnitude of precipitation. You can go back and do all the way to 2000 and then come up with average frequency where you of extreme precipitation events or high precipitation event. It would be interesting to see year 2017, because that's when we had Hurricane Harvey. So here it is. This is 2017. You can see way above normal precipitation. We came up with a threshold of maybe 10 millimeters per day. Here you have close to 200 millimeters per day on 27th of August. All these were extremely heavy precipitation days and resulted in heavy flooding. So by looking at this data, you can come up with precipitation hazard assessment, and combined with socioeconomic data, then you can see which area have more exposure and which are more vulnerable, and I'm going to demonstrate that next. However, I have gone back here and also looked at map over general Texas area by looking at map. So when you go down, here is the map. This is again for August, month of August. And then what you see is high precipitation along this Gulf of Mexico coast. Here is Houston area. And so this is climatological or long-term mean, again between 4 to 5.25 millimeters per day. So this is where we will be looking at where exposure is higher. And so for that, I am going to use QGIS. Okay, so this is a busy graph, but I will walk you through all the layers that we have. And that helps us see this is Houston. Okay, what I have added here is stream data, and as this is long-term mean data that I just showed you, and I downloaded TIFF image from Giovanni. What you see here when you zoom out is that trim precipitation resolution is quarter degree. So you see these boxes here. Here generally there is low rainfall. In Houston area, you can say on an average it varies between about 4 to 5, as we saw, 4 to 5 millimeters per day. How further can we see which area are more exposed and more vulnerable? For that, the one example I'm choosing is population. Now if you zoom in, here is the population. We have used this from CDAC, and we saw that last week. You already have information about how to get this data. I've downloaded this GeoTIFF. This is 2015 population data, and these are the number population density for 5 kilometers. So yellows are 50, and then as you go above, the orange and red are about 2000 to 3000. So when you zoom in, you can see that here is within the city, you have high population centers. If you zoom out, there are suburban areas outside or nearby towns which also have concentrated population. As you can see, these are most exposed areas. So anytime you see heavy precipitation system approaching or occurring, you would be paying attention to here where you have higher population. In addition, we have downloaded this impermeable area in Houston. So here is where water cannot sink into ground. It would either be staying on the surface if there is heavy precipitation. And so all the purple areas shown here, these are percentage of impervious areas. So these are higher impervious surfaces, higher percentage. And so by looking at both impervious surface and population together, say zoom into this area, if you look at where there is higher population and higher impervious surface, that's where you have more chances of waterlogging and more people being affected by that. So this allows you to look at multiple data sets in GIS framework to come up with vulnerability in different areas. We've also looked at SRTM, Shuttle Radar Topography Mission Terrain. I've calculated slope based on that. So anywhere lower the slope, so if you zoom in, this is higher resolution data. This is about 90-meter data. I'm going to zoom into the layer. So here you can see that wherever you see higher slope and then lower slope, these are the lower area compared to these area, and so that's where you would expect more water to come down from a higher slope area. And if you look at where these area where there is impermeable surface, higher percentage of that, so say here, and then look at population where it is higher. So this allows you to combine different data sets to look at the more exposed and more likely flooded communities and areas based on this population, impervious surface data and slope data. This is just for example. You can use other vulnerability data that are available from CDAC or other socioeconomic data if you have them available locally also from at county levels or at smaller town levels. You can put them in GIS framework and analyze along with this precipitation. So finally, what we want to see is, suppose you have forecast. We saw this from GEOS 5. We already know this is month of August and this is 5th of August rainfall. Suppose you go to 10th of August, and if you see what the precipitation looks like, as you can see in Houston area, say for this, there is no chance of very heavy rain. It is way below 10 millimeters per day. You can animate also between 5 and 10 August and see. Okay, so you can see, you can animation, you can slow it down, see whether you expect any rainfall that exceeds our threshold. You do see precipitation system arriving, but they're still in this range. So they're below 10 millimeters per day. So from our past hazard assessment, we know that this range of rainfall is normal for Houston, and if it is normal rainfall, most likely communities and cities have adjusted to that rainfall. It's only when you have very heavy rain in short period, then as we saw in the GIS analysis, there are pockets where there are high population centers, which may be in low slope area where more built up area are there, less impervious, and so those are more vulnerable areas. So this exercise just shows how to work with the data without really downloading. You can do analysis, look at past assessment, look at past, look at forecast precipitation, and by combining information from past, as in this case we looked at mean and standard deviation and the threshold we decided, you can set your threshold according to percentile of rainfall. So there are other statistical techniques that you can use. This was just to give you an overview of how to use these different data sets to come up with good disaster risk assessment related to extreme precipitation and flooding. Now, I also want to point out that we looked at SRTM data, this impervious surface data. These are all described in these webinars we talked about last week. These are ARSET webinars in last 2 years, and they all have information. The disaster scenarios and tropical storms has information about the data sets we have talked about, how to get them, such as SRTM, how to calculate slope, how to get impervious surface data from CDAC, and of course population data. We already saw that. So that's just for your information here. And so what we can conclude from this is that these data in combination with, if you have any in situ or local data, can help in good disaster risk assessment. Also note that trim data we used here are quarter degree resolution, but if you use GPM IMERS data, they are 1/10 of a degree. They are currently not available in Giovanni for entire period, so we have not used it. But you can go to GeoSTISC, download, and do this to the similar analysis, find out mean, standard deviation, and come up with your threshold. One more thing to notice here is that we looked at monthly mean precipitation to come up with our threshold. You can do that on either day-to-day basis. So for each day, you can have 18-year mean value for that day, or you can pick a period which is a week. And that depends on which area you are. And so looking at these data gives you feeling for how precipitation changes in your area and how you want to develop your algorithm to have appropriate hazard assessment first, and then combine it with socioeconomic data to come up with a proper disaster risk assessment. So this concludes our demonstration of this flooding assessment. Also, just before we close this, there is a flooding tool that I want to point out. This is based on MODIS data, and this is the flood mapping. I have picked this 2017 31st of August. If you zoom in, it shows this red area which are flooded. So again, the webinars that I mentioned earlier have details about these tools. But in addition to looking at extreme rainfall, you can look at these flooded area and see, are these area closer to where population centers are? Are there any major infrastructure nearby? So this is further analysis you can do. So this is just for your information. just want to share some more information. Uh, so as I said, you can work with iMerge data, which is slightly higher resolution, about 1/10 of a degree. And so one more thing to clarify here, when we looked at the animation of this forecast, and you can do this for Mozambique cyclone also, you can go back and look at global data and see if there is any storm approaching. If you animate, we did animation and we talked about the range here. As you can see, this is 3-hourly accumulation. So when you compare with the daily precipitation we have from the long-term mean, you will be adjusting those values. So that's one thing I wanted to point out, that you would be looking at um, sort of averaging over entire day and see whether it exceeds 10 millimeter per day or not. But any one event here, of course, is much smaller. So again, it's important to note that what the idea here was to demonstrate how these different data sets, although with different resolution, can aid in disaster risk assessment along with socioeconomic data. And for more quantitative analysis, there is no other way but to actually work with digital data and subset it on your local area and develop algorithm based on some in situ measurements also that aids both hazard assessment and disaster risk assessment. In areas where there are not many in situ data available, these remote sensing and modeling data provide excellent proxy or estimation about what is going on in those areas. So that is brings us to end of this presentation. Next week, what we're going to have is we're going to have 2 guest speakers. First will be from New York Department of State Health Department, and she is going to describe how they use NASA remote sensing and model data for extreme heat or heat stress risk assessment, and how they use that information for helping communities in New York State. Then the second speaker would be from the World Resources Institute. They will demonstrate they have multiple tools. They combine data sets from remote sensing and models, as well as socioeconomic data from CDAC, and they have tools, web-based tools, to look at vulnerability to different disasters. So these 2 guest speakers will be there next week. So we like to conclude today's demonstration, and if you have any questions, we can answer those. There are a couple of things I want to clarify. I've used term climatology. Actually, it's, I would say, long-term mean, because the data record we looked at is 18 years. Usually, if you have climatology, you require about 30 years or so long data. Based on remote sensing, these data sets extend up to 18, 20 years. So that's actually long-term mean is what we have talked about. That's just a clarification. Also, at one point in Giovanni exercise, wind speed was mentioned at millimeters per second, but actually it is meters per second, and my apologies for that mistake. So these are just a couple of correction and clarification, and with that we can go back to the question answer session. Okay, so says for US precipitation data, if I download data, what is the underlying geometry? It appears that some was on country of state boundaries and others were something else. Can you please clarify which data set you're talking about? Are you talking about from Giovanni or so TRIM and GPM precipitation, as I said, resolutions, these are uniformly gridded data. TRIM is a quarter degree, so about 25 kilometers. GPM I merge is 1/10 of a degree, so about 10 kilometers. So um, they basically would give information on those grids, and then you can crop it to the area shape file of your interest, either a county or state. Okay, so what is the resolution of global flood hazard distribution? So that comes from Dartmouth Flood Observatory in slide 13. So the actual resolution would be 250 meters from MODIS, but then there are other slightly higher resolution data also. Whether it is sufficient or not, that depends on the size of watershed or river basin or stream that you are looking at. For major river basins, this works. Yeah, this question is interesting. The climate change is affecting these various weather phenomenon. All of these data are non-stationary, so true. And so is there a site or tool that removes trend? So I am not aware of where data are available without trends. We will look into it if any of those available. But that was the point in showing GES Data and Information Service Center, GISDISC, where you can actually download data and detrend them for your own region. So that is where you need a little bit of quantitative analysis in your own area. Yes, so question 4, that is what I showed for Houston area, but we didn't see that QGIS analysis for Mozambique. But you can exactly use the same information from forecast. If you look at GEOS5 forecast or any meteorological center forecast in Mozambique area, if you see a storm approaching, you can look at the past data and see with respect to that which way it is heading, what intensity it is already in terms of winds and precipitation. So that will allow you and to have some assessment based on forecast data also. Yeah, so question 5, how to calculate IDAI anomaly. And this is somewhat subjective. I picked a threshold which said that, okay, that the rationale was that this is the long-term mean, which is what we calculate from Giovanni. And then standard deviation is the natural variability you observed in this 18-year period. So my logic is that any rainfall that is within that range, so mean plus standard deviation, I would say it is not extreme. It is higher than normal, but still it could be within one standard deviation. Any rainfall that is above that, that is anomalous rainfall. And then you can look at in terms of one standard deviation, two standard deviation, three standard deviation to come up with intensity. So threshold I used mean precipitation at each grid point from Giovanni, added standard deviation for this 18-year to that, and then that was the threshold used. So then I went over lifetime of IDAI, had average precipitation for IDAI, and then subtracted mean and standard deviation threshold from that. That was the anomaly. But you can perhaps examine rainfall in detail and see, based on, say, your in situ damage data, you might come up with a conclusion that, okay, until and unless precipitation is as heavy as 3 standard deviation, our communities can still absorb the hazard intensity. And then you would have alerts or response when rainfall is above that. So that is really dependent on region that you're looking at. I picked this as an example. And I picked the same for Houston flooding also. But then again, that depends on the community or area you're focusing on. How much precipitation, what kind of surface is there? Is there a slope that water can run off quicker than certain intensity rainfall? So these things are very region specific. The idea here is to, through this example, how can you look at different data sets and understand your own region, how hazard intensity is, how they can impact your area. And as I said, this was still somewhat qualitative in the sense we did calculations, but we were still looking at result visually. If you want more detailed quantitative information, you would be analyzing digital data. Is there a public Amazon Web Service simple storage service bucket from which one can access the NASA data? So there are several data which are available through Google Earth Engine, and ARSET is looking into that. That in future we would like to introduce as many data sets as we can through Google Earth Engine or other cloud services. So what is the accuracy of precipitation data or Mozambique, especially of high precipitation rates? There is no simple answer to that. If you look at validation of TRIM or GPM data, they are done on selected regions. So over Mozambique, there is, say, no detailed validation or comparison with any in situ data. So for higher rain rate, also for smaller region, best way is to actually have in situ data and compare with it. There may be biases, but on the other hand, the rain gauge calibrated data, final data, which are iMerge and TRIM final data, they are calibrated with whatever rain gauges are available. So there, on the grid that they have, the biases should be small. Random errors associated with those precipitation estimates, they are available in the data set. If you go back and look at just this that we saw, you will see error estimation. So you can look at that to get more understanding of how accurate the data are. Question 8, it's what I wanted to clarify actually, that TRIM data are quite coarse. Actually, GPM data, which are 10 kilometers, also they are coarse for urban flooding. So for urban flooding, we don't have satellite data which are high resolution enough. We don't, but there are optical images that are used, and I want to show example of this. Moody's near real-time flooding. And again, I would refer to ARSET webinars that we did for tropical storms and also for urban flooding. You can go in here, click into any region, and this provides inundation. This is 250 meters data. Only problem is that, and I'm trying to go to, say, Hurricane Harvey, we can see maybe. I'm just going to pick here. You can see flooding at inundation occurring because of Hurricane Harvey. It's a 250 meter resolution. So actually for flooding, you can not use TRIM or GPM to look at detailed flooding, but it we are looking at it because it gives you idea about extreme precipitation. Now, for actually looking at inundated area or flooding, you need two things. First of all, you need something like this, which tells you that there's flooding, previously dry surface is now flooded, or you have to have a model, flood model, that gives you stream flow into the streams that are going through this region, the Houston region. So that's a challenging thing, but just by looking at precipitation, you will get some idea that if a rain system is heavier than this, and if certain areas are receiving more rain, then you would expect flooding. Over the US, there is good radar coverage, so we can use those. But when you go away, where there are no in situ data, no radar data with continuous space-time coverage, then at least stream and GPM give you some idea of how precipitation may be occurring and maybe causing flood. So that's why we actually looked at SRTM, population, impervious surface, which are higher resolution. These are much higher resolution in few tens of meters. So 30-meter resolution is there for SRTM, 30 meters for impervious surfaces. And if you look at that, it gives you some idea of where the low-lying areas are. So same, even if your precipitation is low resolution, you are able to isolate areas which are more at risk of flooding. Yes, this is the question. I just answered question 9, that over the US, you have high resolution data, you have very good radar coverage, and you would be using that. The idea here was that when there are no such data available, that most of the world, sometimes they don't have good radar coverage. And in that case, satellite data are very useful. So question 10, is the Giovanni tool and its variable available to get information about all countries? Yes. So if the data are global, then you can get for all countries. Now, tool is not limited to some countries. Not only that, if you look at Giovanni spatial subsetting, in addition to countries, you have selected watersheds, major river basins. They are also available. Okay, so this one, TRIM data, as it is tropical rainfall measuring mission, it does not extend in higher latitudes. GPM does now, but TRIM is limited to minus 50 to 50. So outside that, you will not have TMPA data. But GPM will have data for that. You can also use GEOS 5 and MERA2 rainfall globally. What is, okay, so special resolution are listed in the table in the session we saw earlier session. Session 1 has a table which tells you each data set, what resolution is there. It varies, as we talked about it. What type of interpolation methods apply in mapping? Why did you use not ArcGIS? Would like to. Oh, yes. So we use QGIS because it is open source. That's the simple reason. The ArcGIS have many more features. It's perhaps more stable. Also has some data sets available through ArcGIS, but it's not open source. And so that's why we have opted for QGIS. In here, I did not do any interpolation. There are that you can do kriging for precipitation. That would be a good idea. but here there was no interpolation used. Yes, so I would refer to the tropical. Okay, I think let me find a exercise that provides information about converting to slope. So it's a shuttle radar topography mission. I think we will search. There is an online exercise that helps you go through, download SRTM, calculate slope, and get into QGIS. So we will find the link and post it in the question answer session. So this 30, so standard, it is standard to use 30-year minimum period for climatology. So this is for date. I assume you're talking about the climate.gov site where 30-year data were used. We used even shorter period from remote sensing. We don't have 30-year yet. It's close to 20. So we used 18-year in our analysis. But the climate.gov tool that we saw picked 30-year. They used 30-year as their climatology. And that has been recommended that you use at least 3 decades as your reference. Longer is okay, but because there are interannual variability and decadal variability, so if you look at shorter periods, sometimes you are looking at that rather than true mean. Any case of rainfall data and runoff data with stormwater and no stormwater infrastructure conditions for cities. So I think for any city, stormwater and no stormwater infrastructure information should be available. I'm not sure whether CDAC has that, but cities themselves or municipalities might have that information. And then perhaps you can look at rainfall and runoff. We looked at satellite here, but if you look at MERA, that will provide you runoff. There is a land data assimilation system that provides you runoff. Again, I keep pointing back to our ARSET webinars, but all these data sets like runoff and rainfall from land data assimilation, they've been described in the fundamental online webinar. So those are available. You need that infrastructure information or data that NASA doesn't have it. Maybe CDAC may have it, but I haven't seen it. So yes, so each has own raster grid size. That's the resolution we talked about. So the goal here was to present all these data sets and show the tools how you can work with these data in your own region, geographical region. So you can come up with your own methodology. I want to stress that again, that this isn't any standard method that we are presenting. The goal was actually to introduce data and tools, how you can use them. That's the example here shown. So if there are no more questions, we like to thank you for attending today's session, and we hope to see you next Tuesday on 13th of August. We will have 2 guest speakers. Today, I want to thank all my colleagues from ARSET, Sean McCartney, Elizabeth Hook, Brock Blevins, and Selwyn Hudson-Odoi. They all helped in organizing this webinar. So thank you all, and thank you all for attending today's webinar. Oh, and one more thing, sorry about this. We have homework posted on ARSET website. There's a Google form link. So please go to the website and access the homework. And this homework is due by 30th of August. There will be one more homework posted next Thursday at the end of the series.